Good morning. My name is Bo Strickland and I'm an instructor at Red Hat. This morning I would like to share for you a taste of training that comes from our RHCE Rapid Track course. This is a course where we take experienced Linux or Unix administrators, bring them quickly up to speed into the Red Hat way of doing things, and prepare them for the RHCE certification exam. What I would like to talk about this morning is encrypted partitions. In the news, it's not hard to come across stories of lost laptops or lost thumb drives that contain sensitive information, where that information then gets shared with the public. This is a problem which is easy to solve with Red Hat Enterprise Linux 6 using encrypted partitions. As a demonstration, I'm going to be using a Red Hat Enterprise Linux 6 system. I'm going to make use of logical volume management, so I'm going to become root. By performing a volume group scan, I'm going to see that I have about 12 gigs of available space to make use of. That will be plenty. Taking a logical volume scan, I see that I have what looks like a home partition or root partition, maybe a virtualized guest. What I would like to do is create a new logical volume. I'm going to call it my lockbox. And I'm going to make it fairly modest in size, maybe 100 megs, and a member of the volume group vol 0. Running my LVS again, it looks like that has been rounded up to about 128 megs. Just as a quick refresher of how we usually go about using logical volumes or partitions, the next step would be to lay down a file system on dev vol 0 LV lockbox, make a mount point such as mount lockbox, and mount my logical volume to that mount point. And at this point, under mount lockbox, I have a file system using the logical volume that I just created. If I take a history of my commands so that we can come back and talk about them, the general approach is to obtain a partition of some kind, create a file system, and mount it to a mount point. With the encryption layer, it comes in very close to the block layer, making the block device layer, making use of an infrastructure in the kernel that's known as a device mapper. And so after we create the logical volume, but before we lay down the file system, we're now going to add a layer of encryption. In order to do that, let me go ahead and unmount the file system that I just created. Let me become root and unmount the file system that I just created. Let me now take a look at a command that is called crypt setup. Crypt setup is a front-end command for managing the encryption layer. It is a command that has some history to it, and so some of the subcommands that you would think you would be using, such as create and remove and such, are actually legacy commands. And these days people would make use instead of the LUX extensions, and so all of our subcommands are going to start off LUX. LUX format is going to prepare the encrypted layer. LUX open is how you initialize it, or you open your connection to it when you're ready to make use of it. LUX close is how you close it when you're done. Generally, with the encrypted layer, the first step is to initialize it by laying down random data. It ends up people who are smarter than me, if you do not initialize the device that you want to encrypt with random information, then have techniques by which the encryption layer, the encryption algorithms get weakened. And so as a good practice, I'm going to have the kernel generate random data, which I use to initialize the device. While we're waiting for that to happen, if I want to observe what's going on, I should have a CPU that's spending a lot of time down in the kernel coming up with random numbers as this device gets initialized. At this point, we seem to have fully initialized the device. Of course, if you are using a large file system which is gigs in size, this is the type of thing that you do overnight before you go further to prepare your system. Having done that, I'm now going to use the crypt setup command, the subcommand that was called LUX format, specify the device that I would like to initialize, and then a little oddly, I'm going to associate, with LUX format, the device I would like to initialize. It's going to warn me that this is going to clobber any information that's on the device. I'll say that I would like to do it. And this is where I specify my passphrase now, which will need to be specified whenever this partition is to be used. Having initialized it, I can now open my connection by calling LUX open on the initialize the device. And this would need to be done every time that you would like to mount the device. The format step is only done once to initialize it. Open needs to be done whenever you would like to make use of it. I also need to specify an arbitrary name that I'm just going to call lockbox, and this is going to be the representation of the plaintext layer that overlays the encrypted layer underneath it. Of course, in order to open my connection, I need to provide the same passphrase that I provided earlier in formatting the device. The name that I assigned it is going to show up in the dev mapper directory, which is true of all of these virtual devices that are managed by the device mapper layer. As I gave it the name lockbox, its entry is going to be called dev mapper lockbox. And this is what I use to access the plaintext layer, which is overlying the encryption layer. How do we make use of it? We lay down a file system. And so let me lay down a file system on dev mapper lockbox. Let me now mount dev mapper lockbox to the mount lockbox directory. And inside mount lockbox, I have now an encrypted layer, which is using this device mapper front end to protect the file system. If I were to copy RHCE services into my lockbox, then if I were to try to access it using the standard plaintext layer, I should be able to grep HTTP out of mount lockbox services. And of course, we find references to that within the file I just copied. If, however, I unmount my lockbox, I then perform a crypt setup lux close on dev mapper lockbox, the plaintext front end. That's now going to tear down the encrypted layer, where all I have left is the underlying partition, which is LV lockbox. And we should find that if I were to grep HTTP from the underlying device, vol0 LV lockbox, then there's no evidence of that plaintext fragment being found within the encrypted volume. This is the standard approach. Now obviously this is a little bit laborious. If you would like to automate this upon setup, the opening and mounting and closing of the device when you're done, there is a configuration file which is called the crypt setup the crypt tab. Just as you have an RHCE tab file, you can have an RHCE crypt tab file. And this is where you can define the names and the mappings so that this automatically gets mounted on boot up. I won't go through the details of it, but that's available to you if you want to pursue it later. Also, new within Red Hat Enterprise Linux 6, this layer has also been integrated very nicely into Nautilus, or the GNOME file manager, where if I say I would like to browse my computer, notice that it has evidence of the encrypted volume which I just created. In order to open a connection to that volume, I would need to re-specify the password. I can either remember it for this session or store it forever within my personal key ring. And having initialized the connection, in order to actually perform the mount, I need to give root privileges as well. But now I have access to that file system through my desktop. If I am ready to tear it down, then I can just eject it as if it were some other kind of device. And so it's available to you from the browser as well. All right, what I've talked about is encrypted partitions and the idea that you can protect the data on your laptops or other machines so that you only need to provide a password at boot up. And that way, if you leave your laptop within an airport, you'll be protected. This is representative of some of the topics that we talk about within our RHCE Rapid Track Preparation course, which prepares you for the RHCE exam. Thank you.